A trie or a prefix tree is a tree data structure used to efficiently store and retrieve keys in a data set of strings. So what we're being asked here is to implement the trie class, and that includes 4 implementations. The first is to initialize the trie object, and then the other 3 are methods of the trie class. Okay. So first thing we'll do is let's jump through each of these. We'll go through them one by one. That's what we'll do. So let's start with initializing the trie object. Initializing a trie object is essentially the same as initializing any other tree. So you start with a root node. So we'll say root equals, and then we'll set it equal to a node. And usually a node has a class already preset for us. However, this time we're going to be the ones to create the node class. So here is, we're going to call that class trie node, and here is an instance of the trie node. Essentially, every node we create is going to be of this class. It's going to be this type of node. So it's going to have 2 properties. The first is a children property, which is a hash map that initially has no values. And then it has a isWord Boolean that is initially set to false. Okay, so now that we've created this node has those 2 properties. And that is us initializing the trie object. So any tree at the beginning is just a root node. And now we'll move on to the insert method. So we're going to create a method that inserts words into our trie. So we've got a trie node, and I'm going to remove this root equals here. We'll just have this circle. So this represents our root. Any following nodes will be of the same type, but they'll be open just to indicate that they're not the root node. Okay, so when we insert into our trie, what we're going to do is we're going to ask our root node. We always start at the root node when doing anything with a trie. And just the same way we do with a tree. We always start at the root. And you say to the trie, hey, do you have, in your children's hash map, do you have the key B? And at the moment, it has nothing. So we will create a new node, and we will create the key B, and we'll set the key as B, and then the value as the new node we just created, right? So then we traverse to this new node that was just created, and we ask, hey, do you have in your children hash map the key O? And it doesn't, because it was just created, it has nothing. So we create a new node, and we set that key equal to this new node. So to make it clear, now the root in its children hash map has B, and the B is set to this value, which is a node. So it's a reference value, it'll be someplace in memory. And then this node has a children hash map that has a key O, and that value is set to this node right here. So that's what's going on. So we'll say to this node, hey, do you have the key X? No, you don't? Okay, so we'll create a new node, and we'll set the key of X to the value of this new node. And that's what this is resembling here, by the way. So if this node, for example, had an A, it would be like this. This would be the key, or rather, to make it more clear, this would be the key, the A, and then the value would be the node. So whenever we see this, these lines and stuff, it's just the setting of the key, which is the letter, and then the value, which is whatever node that letter points to. Okay, so we'll go ahead and do this for the rest of these nodes. Since this is a new trie, none of these letters are going to exist, right, inside of the new node, or inside of this trie, rather. Inside of this trie. Okay, so we have finished that. And keep in mind, as we're going through and adding all these new letters, all these new nodes to our trie, we are actually iterating through the word. So once we get to G, we know we're at the end of the string, right? We'll be running through some sort of for loop that goes the length of the string. And that'll let us know that we're at the end of the word at this particular point. So when we get to this position right here, this node, we know that we're at the end of the string. We know that this is the last letter. This is the last letter in the word, or rather, this is the last letter in the word. And so we want to mark this node with isWord equals true. We want to set it equal to true. Literally, we will set it equal to true, or uppercase T in Python, whatever it is. We'll set it equal to true. And to resemble that here on this visual demonstration, we will put an asterisk in the middle of that node. So that asterisk indicates that this node is true, or this node's isWord property is set to true. Okay, so what we'll do next is we'll add the word boxer and box. But before that, it's important to notice something here. Each node actually doesn't know its own value. The root node, it doesn't know its value. These nodes, they don't have a value property. The only way you could find the value of a node is through its parent. So for example, this node right here, it's the B node coming from the root node, but it has no idea that it's the B node. The only way to find that information is to go to the root node's children hash map and then see where the B key points to, right? And it points to this node. So it's an important distinction just to understand that each node actually doesn't know its own value, which can at first seem tricky. So now let's go ahead and add boxer. So we'll add boxer. So we're still on this insert method, right? And we say to the root, hey, do you have a B key in your children hash map? Yes. Okay, point us to that node. So we get pointed to that node, and we basically do the same thing for each letter. We go to O, then we go to X, and then when we're at X, we say, hey, do you have the E key in your children hash map? It says, nope, just the I key. And so no problem. We'll create the E key, and we'll set it equal to this new node. And then we ask that node, hey, do you have the R key? No, you do not. Okay, so we'll create this new node, and we'll set that equal to the R key. Okay, so that is inserting. So that's how we insert. And the same way we tracked along with the boxing string, we would have iterated using a for loop of some sort to get to the final. When we got to the final letter, we know we're at the final letter because we're at the end of our string here. So we can set this node's isWord value to true. So now we know that boxing and boxer have been added to this trie, right? Notice though, something's interesting here. The word box is in the trie, yet it doesn't have an isWord value set to true. This is where the isWord property is important. So let's actually move on to the search method, right? We'll add box in later. So we'll add box as a word in later. But let's go to the search method. And in the search method, the way that works is we start at the root node, like we do with any other method of a trie. And we say, hey, do you have B in your as a key in your hash map? Yes? Okay, please point us to that value. And so we do the same thing for B, we do the same thing for O, we do the same thing for, or we get to X, right? We're at the end of our for loop as we iterate through the string box. And when we're at this last point here, we know to say, okay, does this node have isWord set to true? And as we see, it doesn't. So we would return false, right? Because we're checking, what search is checking is to see if the word box has explicitly been added to this try. And even though it exists as a prefix to the word boxing or boxer, boxing and boxer, it isn't a explicit word in itself. It was never explicitly added to the hash map. So that's why it would return false here. Now, if we checked, I don't know, the word bat, for example, if we check the word bat, we'll start with root node. We'll say, hey, do you have B? Yes. We get to B. We're like, hey, do you have A? It says no. We're like, okay, return false. So in that case, we would also return false. Now we'll add box. We'll add the word, we'll add the word box. So we'll insert the word box. So let's go ahead and do that. So we'll do you have B? Yes. Do you have O? Yes. Do you have X? Yes. And so we get down here, and we set the isWord equal to true. And so now if we were to check, if we were to do the search on box, we would find out that it does exist, because when we finally got to this place, this node, the isWord property is set to true, and therefore it would return true. Okay, so now let's move on to startsWith, right? Let's do startsWith, and we'll check for bow. That's what we'll check for. Does the try have a prefix of bow? And I mean, as we can see, it does. But the point of this is, so we'll do the exact same thing we just did with search. We'll say, hey root, do you have B key in your children hash map? Yes. Hey, and this is an O, by the way, not an A. So O. So hey root, do you have B in your children hash map? Yes. Hey B, do you have O in your children hash map? Yes. So we get to here, right? And once we get here, we return true. We return true. We don't need to check if it's a word. We don't need anything else. It just needs to exist from the root down. So if we were checking ba, let's say we were checking ba, we start here. Hey, do you have B in your children hash map? Yes. We get to this node that resembles B, essentially. We say, hey, do you have do you have A in your children as a key in your children's hash map? No. Okay. We return false. We return false. So that's how that works. So now that we've covered all the 4 implementations of the try class, let's look at the space-time complexity of these 3 methods of insert, search, and startsWith. So insert is going to have a space-time complexity of O of n. And the reason it has a space-time complexity of O of n is because, let's say we add boxing in. Well, that is creating n new nodes. So the string boxing's length is n, and therefore it creates n new nodes in the try. And it also takes n iterations to add this word into our try. So that's what the time complexity is there. So they're both O of n. Now you might get a case where we added in boxing and then we wanted to add in box, and we didn't have to add any new nodes. But in the worst case scenario, which is big O notation, it is big O of n. Okay, so now let's move on to search. So search, and the space complexity here. So the space complexity is O of 1. And the time complexity is O of n. Now the reason is, let's say we are searching for the word boxing. We have to iterate through the entire word to see if the last node has an isWord value of true. So that time complexity will be O of n. The space complexity is O of 1 because we're not adding anything new to the try. It's a read operation. So therefore we're not adding any new nodes, and the space complexity is therefore constant. Lastly, we have startsWith. StartsWith, and this is going to have the same space and time complexity as search. So space complexity, we're just searching for a prefix. So, if we're looking for box, we go 1, 2, 3, and we see that that box exists as a prefix inside of this try, and therefore we're not adding anything new, and our space complexity is constant. It's just 1. And then the time complexity is big O of n, and the reason for that is because we are traversing through the tree n amount of times, the prefix length amount of times, to see if that prefix exists in the try. Okay, so those are the 4 implementations inside the try class. Now let's hop into the code editor and code them out in JavaScript and Python. So what we want to do first is initialize the try object. So we can do that by setting this.root, so this.root equal to a new try node, right? Because every tree starts off as a single node. And then what we want to do is actually create this try node class. So class try node, and then in our constructor function, we want to add the 2 properties, this dot children equals an empty object, which is what we use to implement our hash map, and then this dot is word, which we will set to false. So by default, when we create a new try node, these properties will be set. Okay, great. So now let's create the 3 methods of this try class. And I know it says prototype method or prototype dot insert. It's a little bit confusing. It doesn't look as pretty as having a try class with the insert function inside of it, but essentially these prototypal methods are of the try class. That's how you can think of this. So the first thing we want to do is get the node or the root. So we'll get the root by saying this.root. We'll set it equal to a node. Okay. From there, we'll want to iterate through our word. So we'll say for character of word. And remember, we want to check. First thing we want to do is we want to check to see if node dot children at this character exists, and if it does, we want to traverse the node. If it doesn't, we want to add a new node or add a new child node to our children hash map, right? Add a new key value pair to a children hash map. So what we can do is we can, in order to implement this, we can say let child and let child equal node at children dot character, and we can use a nullish coalescing operator here, which is a fancy way of saying if this is undefined or null, then we will return a new try node. So if this is undefined or null, we will return this here. And if this is anything but undefined or null, we will return whatever this value is. So there we go. Now what we'll do is we will set the key value pair, we'll set the value of the key to be this child. So node.children equals, or node.children at the particular character at equals child. You might be wondering, well, if it already exists, why are we recreating its value? Why are we re-adding it to the hash map or to the object? And it's simply because it allows us to write shorter code. So basically, if the child exists, we will set it equal to itself. That's exactly what we're doing here. And if it doesn't exist, we'll set it to a new try node. And once we do that, that's when we want to then traverse. So we'll say node, which is our current node, equals child. And there we go. So once we iterate through all of the characters in the word, once we get to the end, we want to set the nodes.isWord method, our property, equal to true. So that is to say that, we've added this exact word. Remember when we added boxing, we added boxing, box exists inside of boxing, but we've only ever explicitly added the word boxing. And that's what this marker is for. That's what this isWord property is for. Okay, and then lastly, we can actually, instead of saying let node equal this dot root, we can set that inside of our parameters. And I think that makes it a little bit neater. All of the data that we're taking for this function is getting passed in through the parameters now, which is pretty cool. Okay, so let's do that for the next method we've got to create. And we can actually copy and paste because a lot of this is going to be very similar. So we've got, what we want to do is iterate through all the characters in the word. And if a child doesn't exist, we want to return false, right? So what we can do is, instead of creating a new node, we can just return null, right? And when I say return null, this is going to return null and set it into the child variable, but it's not going to return from the function. So we have to return, we actually have to say if child does not exist, or if child is not truthy, and so if it's null, this will, whatever after this will run, we want to return false, right? Because this search method returns true or false. So we want to return false. And then after that, we actually don't want to reset anything, because remember, we're reading only in this method. We're not writing anything new. So we can get rid of that. And then this just allows us to traverse through the try. And we want to return here, we want to return, if we've made it this far and every character has existed, we've never returned false, then we want to return the value of the isWord property of our node. So node.isWord. So this node at this point, after the for loop, resembles the final node in the try for this word. And so we want to check, is word equal to true, or is it equal to false? And just by returning this, it'll be either true or false. Okay. Now we can for the next method, we can do roughly the same thing. It's very, very similar. The indentation isn't great, but that does not matter in JavaScript. Okay, so what we'll do here is, there's only one difference. It's a very small difference. Remember, if it starts with, if the prefix exists inside of the try, we want to return true, right? So if we make it all the way through, this is actually character of prefix, right? Character of the string prefix. If we make it through all of these nodes without returning false, meaning all of the nodes have a key of this character in their children hash map, then we will continue iterating through. We won't return false. So we iterate through the whole prefix, and if we make it to the end, we want to return true, right? Okay, so here's the entire code. And now let's go ahead and run it. Make sure that it works. Great. So it looks like it's going to work. Awesome. Okay. So that's how you solve it in JavaScript. All right. So the first thing we want to do is get rid of this, go back to the description. We want to initialize the try object. So what we'll do is we will say self.root equals try node, right? And so what we need to do is create that. We actually need to create that class. So we'll create class try node, and in it we'll have a constructor. So def init, pass in self, and self dot children will be equal to an empty map, and self dot isWord will be equal to the Boolean value false, uppercase L. All right. So now that we've done that, let's go ahead and actually implement our methods of the try class. So first we want to do is we want to grab that root, right? We want to grab that root and set it equal to node. So node equals self.root. And then we want to open up a for loop. So for character in word, what do we want to do? So for character in word, we want to check to see if the current node has the character as a key in its hash and its children hash map. So we will say if character is not in node.children, right? It's a little bit different than JavaScript. Now what we're doing is we're checking to see if the character is not in node.children, then we will not return anything. We will set node.children at the character key equal to a new try node, right? Oh, not a new try node, because that's JavaScript. So we set it equal to a try node, and then we will move to that node. So we'll move to that child node, or traverse to that child node, right? And so we'll say node equals node dot children at character, and that'll get us to iterate through to the next node. And then after we iterate through all the nodes and we add all the try nodes, all the characters if they didn't exist in the try, when we get to the end of the for loop, we want to then set the current node, which is the last node, in the word, right? It's the last character in the word, or resembles the last character in the word. Node.isWord equals true. It equals true, right? And so that is the insert method. Now let's go ahead and copy this. We can actually bring it over to search, and it's going to be very similar. We want to first start traversing at the root node. So we set node equal to root. Then we have a for loop that runs for every character in the word. And if character is not in node.children, what do we want to do? It's actually nice and simple. We just want to return false. So if we're looking for a word, if we're looking for the word bat inside a trie that only has boxing and boxer inserted into it, when we ask the B node, when we ask the node that represents B for the if it has the A key in its children's hash map, it'll say no, and so therefore return false. And if we make it through the entire for loop, then the last thing we want to check, or we can check it in this way. We can say return node.isWord. So we're making sure that, remember, we're returning a Boolean, true or false, and we want to return the node, we want to return the value of the isWord. So if this word that we're searching for has been explicitly inserted into the node with our insert method, then its last node would have been, its last node's isWord property would have been set to true. So we return that. That lets us know if the word has been explicitly inserted into the trie before. And we can now take this information, we can take this code, we can actually paste it right into our startsWith, because these functions are very, very similar. The only difference in these functions is that we're checking through the prefix, not the word, given the prefix, not the word. And so we check through the prefix, and we want to return false if any of the nodes don't have the character as a key in their children hash map, just like we do with search. Yet, if we make it to the end, and a word and this prefix exists inside the trie, we don't even care if it's a word or not. We just want to return true, uppercase T. We just want to return true. So if this prefix exists inside the trie, even if it's not a word, even if it's not explicitly a word, we return true. And so let's zoom out a little bit, see if I can show you the whole code here. Okay, so there it is. Maybe I should show you this after it works, but we're going to go ahead and run it. Oh, it just looks like it's indentation error. Same with this. So there might be a few more indentation errors. Yep. Okay. Okay. Trie node object, did you mean children? If character is not in node.children, the trie node object has no attributes children. Okay, so I misspelled children up here. There we go. So the run worked, and now let's submit it. There it is. And that's it. That's how you implement a trie prefix tree in both JavaScript and Python.